Welcome to this series of tutorials on Computree. We will explore the different types of data usable in Computree. In addition to data types, you will discover that Computree is software designed to process and analyze data primarily in forest environments. We will see that the types of data you can use with Computree are, for example, three-dimensional point clouds derived from LiDAR or photogrammetry. It is a free and collaborative tool designed for forestry and environmental professionals. Let's now discover airborne LiDAR. How do we collect these famous 3D data from a drone or an airplane? How do we process them, and why has the last format become the global standard for storing these point clouds? Airborne LiDAR is a technology that allows mapping the ground and objects in 3D using a laser sensor mounted on a drone or an airplane. Airborne LiDAR uses laser pulses to scan the ground surface. We obtain what is called a 3D point cloud. The system measures the time each pulse takes to return, which allows for precise calculation of the distance, and thus the 3D position of the point hit. By combining millions of points, we get a point cloud that represents the terrain's surface and everything on it. What is the LiDAR composed of? It is an assembly of 4 high-precision sensors. The laser sensor emits light pulses in all directions, often using a rotating mirror to scan the entire environment. The inertial navigation system measures in real time all the movements of the system like roll, pitch, and yaw to correct the position of the captured points. The precision GPS records the exact position of the sensor in space in X, Y, and Z using GNSS satellite data. Finally, a microcomputer. It collects, processes, and stores all the acquired data. After the flight and pre-processing of the data, we obtain several files. The main file in LAS format contains all the points of the 3D cloud. A trajectory file, often in POS or TXT format, which records the position and orientation of the plane or drone at each moment. Sometimes ground control points GCP to verify the accuracy of this survey. Here is what a raw LiDAR file looks like. Each point represents a measurement. Colored here by altitude, this cloud can then be processed to create maps, models, or thematic analyses. In addition to airborne LiDAR, Computree can utilize other types of three-dimensional data depending on the project's needs. Terrestrial LiDAR, or TLS, is a ground-based measurement technology using a laser scanner mounted on a tripod. It allows capturing scenes with very high resolution, which is particularly useful for analyzing in detail trunks, low branches, ground vegetation, or structures like buildings. Among its advantages is a very detailed description of objects. The point density per square meter is much higher than in other types of LiDAR, which offers unmatched precision over short distances. But this precision comes at a cost. The terrestrial laser scanning has a limited range, requires multiple measurement stations to cover a complete area. The TLS is therefore ideal for surveys with a small special footprint when detailed precision is a priority, such as in forest growth studies, trunk inventory, or digitizing forest infrastructures. But then what are the differences between airborne LiDAR and terrestrial LiDAR? Airborne LiDAR is an ideal technology for mapping large areas, such as extensive forest zones or areas difficult to access on the ground, like steep slopes or very dense environments. Terrestrial LiDAR is ideal for precise localized studies such as detailed inventories, precision measurements on vegetation, or architectural surveys. Installed on the ground, this type of scanner captures very fine details, perfect for analyzing complex structures, whether in the forest or in urban environments. Mobile LiDAR, also called MLS, relies on sensors mounted on a vehicle or carried like a backpack. It provides an excellent compromise between precision and speed of coverage. On the advantages side, it allows for rapid mapping of significantly larger areas than terrestrial LiDAR, even in complex environments like cities or dense forests. It produces dense and precise data while being more flexible than terrestrial LiDAR. But beware of the drawbacks. The data quality can be affected by the speed of movement, vibrations of the support, or obstruction by moving objects like cars or pedestrians. Its use is therefore particularly relevant for urban surveys, roads, or forest inventories on areas from a few hectares to a few dozen hectares. The covered areas remain very limited compared to airborne LiDAR. Aerial photogrammetry is a technique that allows for the reconstruction of a 3D point cloud from simple images taken from a drone or an airplane. Thanks to correlation algorithms, the software compares several views of the same object from different angles to deduce its three-dimensional shape. It is a more economical method than LiDAR because it does not require specialized sensors. A drone equipped with a camera is enough. This allows for the rapid mapping of large areas and obtaining orthophotos as well as digital surface models. But be careful, unlike LiDAR, photogrammetry does not allow you to see through vegetation. It therefore does not provide access to the soil structure under the canopy, nor to the actual height of trees or lower layers. Another important limitation is that it is not a direct measurement like with a laser, but a geometric estimation based on image comparison. This makes the method less precise, especially in low-contrast areas, under vegetation, or in suboptimal shooting conditions. In summary, aerial photogrammetry is a good compromise for open areas and low-budget projects, but it does not match the precision and vertical analysis capability of LiDAR. We can also use 3D models created from stereo satellite images. This involves applying photogrammetry methods to satellite images. This method provides an overview of very large areas, but with generally less precision than LiDAR or aerial photogrammetry. The principle is similar to that used with airplanes or drones. By combining several images taken from different angles, a three-dimensional model of the terrain can be reconstructed. Let's now move on to the presentation of the LAS format, a global standard for storing and exchanging LiDAR data. The LAS format is the global standard for storing and exchanging LiDAR data. It is a binary format, so it is very compact and quick to read even for files containing millions of points. Each LAS file contains in particular the XYZ coordinates of each point, the laser return intensity, the return number. For example, first or last return to pass through vegetation, the GPS time, the scan angle, the point classification, ground, vegetation, building, etc. The LAS also contains a header with metadata, flight date, projection system, number of points, etc. This is what allows any compatible software to open and process these files, ensuring interoperability among all geomatic stakeholders. Note that LAS files can be very large. To reduce their size, the compressed LAZ format is often used, which retains all the information, but significantly reduces the file size. Computree is capable of reading these two file formats. In this section, we will explore 3 essential digital models derived from LiDAR data that can be produced and visualized in Computree: the DTM, the DSM, and the CHM. You'll see it's simple to understand and essential for getting started. 3 digital models are commonly used: the DTM, DSM, and CHM. First, the DTM, or Digital Terrain Model. It's a map of the natural relief. Imagine removing all the trees and houses. Only the bare ground remains. The DTM, that's it, the terrain model with nothing on it. Then there is the DSM, the Digital Surface Model. It represents everything on the surface, the ground, but also the trees, the buildings. That is everything seen from the sky. Finally, the CHM, or Digital Height Model. It is simply the difference between the DSM and the DTM. It gives the height of objects relative to the ground, like the size of trees or buildings. That was the 3 digital models presented: Digital Terrain Model, Digital Surface Model, and Digital Height Model, or what we call rasters. But what is a raster? A raster is an image. More precisely, it's what we imagine when we think of a digital image, a grid of pixels, each representing information. After collecting LiDAR data, you get a point cloud, millions of 3-dimensional points representing the ground, vegetation, or buildings. To make this data easier to analyze, it is transformed into a raster image. How does it work? The area is divided into small regular squares, forming a horizontal grid. In each cell, the points present are examined and information is extracted. For example, the ground elevation for the digital terrain model, the elevation of vegetation or buildings for the digital surface model, the height of vegetation for the normalized difference vegetation index. Rasters can also be used to store other types of values, such as the number of points, for example. These values are stored in each pixel of the image and can be translated into color, thus providing an image that allows mapping the information of interest. It is this transformation that allows the transition from a complex cloud to a clear and readable map, easier to utilize. Thanks to the raster, you can then perform precise terrain analysis, such as identifying tree heights, detecting open areas, or visualizing relief variations. Feel free to ask your questions in the comments or on our Discord channel. See you soon!